Today's synopsis article: Verification in the AI era, scaling to quadrillions of cycles of the software-driven hardware-assisted verification. The industry challenge. The semiconductor industry is at a pivotal moment, with $192.7 billion in venture capital flowing into AI in 2025. The demand for verification platforms that match rapid innovation cycles is surging. As AI, multi-die architectures, and edge computing drive exponential complexity, traditional verification methods struggle to keep pace with the requirements spanning IP, subsystems, chiplets, and multi-die verification for AI-driven workloads. Hardware-assisted verification (HAV) is essential for ensuring functionality, power, and performance. Design teams must optimize the total cost of ownership by investing in the future-proof verification systems, addressing scalability for emulation of the largest AI chips and enabling verification hardware to be reused across emulation and prototyping use cases. While new verification hardware for emulation and prototyping is critical for boosting productivity, the associated workload application software is now even more critical. New hardware must enable contiguous scaling, increasing throughput, and expanded use cases in existing hardware, accelerating time to market. Just as software-defined advances transformed the smartphone, automotive, data centers, and networking and IoT, we have now entered the era of software-defined hardware-assisted verification (HAV). Compounding verification challenges. So why is that such a big deal? To better understand today's verification challenges, let's have a look at the figure 1, below, which illustrates the compounding complexity increases across software, hardware interfaces, and verification use cases. Figure 1. Compounding verification challenges. Image synopsis, AI and memory war. So, let's dig a bit deeper into this. AI applications are characterized by software programs, code workloads, and large language models (LLMs). Workload complexity is defined by the lines of software. And while software applications have become more specific and thus contained to certain specialized tasks like AI training versus inferencing, or the creation of text versus images as video and etc. Within that scope, software complexity continues to grow as end users expect more from these AI applications, and they thus evolve very rapidly to stay competitive. In addition, we are facing a little wave of the AI LLMs serving generative AI and inferencing needs from the data center to the edge, with models doubling in size every 4 months. Figure 2. Tidal wave of AI training. Search visual capitalist at years of consumer AI deployment in one giant timeline. This also means that the competed in today's world of ever more complex and specialized applications, customized hardware is required to meet functionality, power, and performance metrics. Conversely, hardware needs to be scaled enough to support a variety of applications and be future-proof for a couple of years to handle the AI algorithms of tomorrow. Let's take NVIDIA as an example. After the announcement of Blackwell, NVIDIA announced the Rubin AI platform and the Rubin Ultra family to be available in 2026 and 2027, respectively. In the Rubin CPX architecture, public built for massive context inference applications was announced in September 2025. NVIDIA also reported massive software-driven improvement for existing hardware products, including 2 times Blackwell performance since its launch, 4 times performance improvement for Hopper during its lifetime so far, and 6 times better throughput enabled by the Dynamo software. For end users, this yielded at the system level 2 to 4 times speedup on Llama, up to a 6 times improvement in the first token latency and 3 times higher token output. So hardware and software grow more complex and become more specialized, but at the same time, software-defined systems ensure that the software upgrades can be made during the lifetime of the hardware, complicating the matters to design silicon for these software-defined soft systems, as the fact that Moore's law has been facing physical limitations and the way to scale to bigger designs has been multi-die systems. While the creation of each die resembles the development and verification of SoC, putting the different chiplets together creates its own unique challenges, and hardware is still doubling in size every 18 months because of more than more innovations. Added, added to that increasing chiplets will come from different vendors introducing ecosystem plays requiring coordination on communication protocol and verification methodologies. As a result, rapid evolution is of interface IP implementing these communication protocols has become a crucial contributor to verification complexity. To feed more data into AI algorithms to provide a more intelligent insights or autonomously perform specific tasks, communication protocols evolving in astro, astounding pace as illustrated in Figure 3, now doubling in bandwidth every 2 years. Figure 3 PCIe and Ethernet evolution. Furthermore, all this data has to be stored and read back at every fast pace to reduce the lag between a request to an AI bot or agent and the actual section. The innovation in memory architectures, as illustrated in Figure 4, has been critical to push forward the ability to support the latest AI computing architectures. Finally, the use cases define the scope of what needs to be verified, and more use cases are emerging at the record pace because of pressure to characterize and optimize the end product with workloads running. Not only is software complexity growing faster than ever before, driving new demands on multi-die system calling and interface IP protocol innovation, the pace at which new silicon is coming out has also increased rapidly to stay competitive in this fast evolving AI landscape. This is forcing developers to look to shift left their software or hardware verification and validation to meet time to market requirements and avoid silicon spins. As a result, the scope of verification continues to dramatically grow to ensure that the key metric on functionality, power, performance, throughput, latency, security, safety, scalability, and many more are meeting product requirements. This has led to new verification use cases requirement to pull in most of the tasks to the pre-silicon phase. A new era of hardware-assisted verification. The growing complexity of software, hardware, and interfaces, combined with expanding free silicon use cases, is driving the demand for quadrillions of verification cycles. And not all these cycles are equal. For example, there is a different requirement for RTL verification versus software validation versus performance validation, which means that just like in the AI space, there is both a need for more specialized verification hardware. For example, when it comes to the maximum capacity that needs to be supported, as well as a need to have the verification hardware be more flexible and future-proof to handle a growing and changing set of verification requirements. Just as software-driven updates continuously enhance data centers and vehicles, we are now in the era of software-defined hardware-assisted verification with the requirement to be delivering on ongoing improvement and flexibility. At Synopsys, we are committed to empowering innovation through a continuous re-engineering, and we have engineered our hardware-assisted verification systems with the future in mind. Our software-defined AHV solution enabled engineers to scale verification across industries, meeting ever-expanding pre-silicon demands. Software-defined AHV is transforming verification. Let's make progress together on one software improvement at a time. Thank you for your time. See you next time.